In this video, we are going over the E2 reaction. Now, E2 stands for elimination, bimolecular. So the E stands for elimination. And the 2, which is similar to the SN2, this means the rate determining step is bimolecular. I'm going to show you a reaction for an E2 elimination. So let's draw one out. So we do need a carbon with a leaving group, and I'm going to use an alkyl bromide. Now I'm using a carbon with a leaving group here. This alpha carbon is tertiary right now. Just something to note. We're going to talk more in detail about this. I'm going to use sodium ethoxide, and the solvent is ethanol. Solvent just helps make sure everything stays in solution. Now, what I've drawn here for the sodium ethoxide, you'll notice that we have a sodium. And anytime that we see sodium or potassium or lithium, we know we're going to drop plus charge on top of this and then a minus charge on the atom right beside it. We can draw this ionic bond as neutral, but really there are charges there, okay? Now, this oxygen has those 3 lone pairs. And we know that we've seen this before. This is a really good base, right? It's also a good nucleophile. And I'm putting this on here now because we will talk about how the E2 and the SN2 reaction compete with each other. Let's focus on the E2 here. We have a good base, a good nucleophile. Here's our solvent. Let me change that to a yellow color. There we go. And let's focus now in on the even more important part, which is our leaving group. Our leaving group here is this bromine. Okay, so we've got an alpha carbon here with a tertiary carbon center. Now, based on what we've looked at already, we've looked at SN1 and SN2. Now, SN1 requires that tertiary carbon with a leaving group. It's so happy to make a carbocation. Remember, these are when we make carbocations. However, we have a really good base, all right? So this base is strong enough to where it doesn't wait for a carbocation to form, all right? So in this case, when you have a base that is very good, you're not going to get SN1. That base is not going to wait around for a carbocation to form. Now, if we look at SN2 as an option, the problem here is that tertiary does not work. Okay, so the issue here with SN2 is that tertiary alpha carbons are no good. And the problem with the SN1 is that we have a really strong base. So these are the reasons why neither one of these is going to work. That's why we're going to do an E2. Let me show you the mechanism here. On this beta carbon, the carbon that's one away from the alpha carbon, we have 3 hydrogens. We are going to do an elimination reaction. I'm going to show you this in blue arrows here. What's going to happen is that our oxygen of our ethoxide is going to act as a base. It's going to pick up this proton on the beta carbon. The electrons between this hydrogen and this carbon here, that beta carbon, are now going to move in between the alpha and the beta carbon. This is going to form a new double bond. Our leaving group is very predictable. It leaves, all right? Let's draw the product of what we have. So we have just made a new double bond, and we lost bromide ion. Okay, this bromide anion. And then we formed more ethanol, which is just really more solvent. Okay, this reaction is irreversible. And this mechanism is concerted. Now, concerted just means that it all happens at the same time. This is just like SN2. Let's redraw the mechanism here in a nice clean way without any of those markings. All right. Ethoxide. We're going to take a green arrow this time. I'm going to draw out my proton here. What I'm drawing is I'm going to pick up the proton, the electrons fold down, and then we kick out bromine. You might find it useful as you start to do these to count your carbons. So we have 1, 2, okay, 3, 4. The carbons 1 and 2 ended up getting a new bond. And that's indicated with this arrow here. That's that new double bond that forms. All right, so between 1 and 2, we have a double bond. Okay, and then there's 3 and 4, and I can label them here. 1, 2, and then 3 and 4. Okay, cool. E2 reactions make alkenes. That's what we just learned. Pretty neat. These make alkenes. Now, it's not just that simple, and we all know that. There's more involved with this. What we're going to do now is we're going to look at the requirements for an E2 reaction, and then later on, we're going to talk about this whole E2 SN2 competition. Let's write this down so that way we know to review it. E2/SN2, they compete. The example I showed you here was this tertiary carbon. All right, so no SN2 happens, but there are cases when we can get competition. Okay, so this is just the general mechanism. Let's go into more depth about the requirements for an E2 reaction. The first requirement is we need a good leaving group. On an sp3 carbon, okay? Now, good leaving groups are very similar to what we saw. It's similar to SN1 or SN2. Iodine is a great leaving group, and it's better than bromine, which is better than chlorine. Fluorine is not a good leaving group. A tosylate's a great leaving group, as well as a mesylate or a triflate. Now remember that these are conjugate bases of strong acids. These anions are happy to hold that negative charge. The second requirement is that we need a moderate to strong base. Moderate to strong base. When I say a moderate base, we're talking about a conjugate acid of a pKa of around, let's write this out, conjugate pKa of around 10. And if it's a strong base, we're thinking of this conjugate pKa, the acid, conjugate acid pKa of around 15 or more. So in the case of our previous example, that ethoxide, remember that its conjugate acid would be that alcohol, and we know that has a pKa of around 15. That's why this is strong. The third requirement for an E2 reaction is that we not only need a leaving group, but we need a proton that is anticoplanar. And this is going to be on the beta carbon. Now, what the heck does anticoplanar mean? Well, we'll talk about it here. So it needs to have that proton. It's trying to make that double bond. So on the beta carbon, it needs to have a proton that can be abstracted. All right, let's talk about this anticoplanar. I'm going to redraw the first example we talked about. Now, we know that this isn't a chiral center, and so you can just draw them using lines, but I'm going to show it here with the wedge and the dash because it's really going to make it more clear about where this proton is and what the heck does anticoplanar mean. Anticoplanar means that this hydrogen, okay, this is our beta carbon, here's our alpha carbon, and this bromine, this has a dihedral angle of 180 degrees. What I'm going to do is I'm going to rotate this molecule so that we can see it a little easier. And then we're going to draw a Newman projection. So I'm just going to rotate this. I don't know about you, but my brain works better when we're looking at it this way so that we can draw our Newman projection. We have two methyls coming off of this carbon here. Let's label our alpha and beta carbon. Here's our alpha carbon. Here's our beta carbon. The alpha has the leaving group. Okay, let's draw a Newman projection looking down this beta carbon. There's my eyeball. We're looking down this beta carbon. So for Newman projection, I'm going to just draw the circle here. The hydrogen, which is this one, is going down, okay? And this carbon, let's label it. It is our beta carbon. There are two more protons coming out this way. So perhaps I should label this hydrogen here pink. Cool. All right, that's the beta carbon. And right behind the beta carbon on the Newman projection is our alpha carbon. The bromine here is going up. Cool. And then we have two CH3 groups. Great. Let's check this out. Hydrogen to our beta carbon, to our alpha carbon, to our bromine. This has a dihedral angle of 180 degrees. Now remember, this dihedral angle is really just talking about the hydrogen to the beta carbon, to the alpha carbon, to the bromine. All right, so it's really just looking at those four atoms and the relationship in space with regards to their bonds. This anticoplanar is super necessary because of, guess what? Molecular orbital theory. It's coming back. I'm just going to write orbitals with an exclamation point because it's super important. In particular, this is due to hyperconjugation. But really also this orbital overlap. All right, let's look at it. All right, so we're going to redraw this here. Here's my leaving group. This is the hydrogen that's going to leave. This one has two methyls coming off of it. And what I'm going to do here is I'm going to draw the orbitals here. So our hydrogen we know has a 1s orbital. And this is an sp3 hybridized carbon. So I'm going to draw an sp3 hybridized orbital. And this carbon, this alpha carbon here, we're going to draw the antibonding CBr bond. So remember, antibonding has that node. And this antibonding, so it's going to be shaded on this side, and for the bromine, it won't be shaded. There we go. We've got our node there in the middle. This CH bond, I'm going to put the two electrons here in this pink, okay? This is filled. Hyperconjugation says that we can get donation from a CH bond. This is a sigma CH bond. Donation into this sigma star CBr bond. This is actually going to help make that bond break, okay? Now, this orbital overlap is super important because if I have a base with whatever its orbital looks like, okay, think about this base coming in, and as it takes this proton, these electrons need to go into the antibonding orbital. This is now going to allow us to break that CBr bond. This orbital overlap allows this reaction to occur to make our new double bond, okay? And so it's the orbital overlap and due to hyperconjugation that this anticoplanar, meaning dihedral angle of 180 degrees for our hydrogen of interest, which will be opposite to our bromine here. So anticoplanar simply means dihedral angle of 180 degrees from the hydrogen of interest to this bromine. So anticoplanar just means that the hydrogen that we're going to pluck off needs to be opposite of the bromine, and that dihedral angle needs to be 180 degrees. Let's talk about an example where we could have different regioselectivity. Remember that regioselectivity is just kind of where at on the molecule the reaction is occurring. Let's use sodium methoxide again. Remember, we know that this is negatively charged, and if we see sodium, potassium, lithium, we're going to put a positive charge there. We have a carbon here that again is tertiary, but the difference here is that they're not all methyl groups. This means we could get two different alkene products. Let's just make sure. Let's label our alpha carbon. There it is, right there, carbon with the leaving group. And let's label our beta carbons here. We've got a beta carbon here, a beta carbon here, and we also have a beta carbon on this group, that ethyl group, right? Notice I've used two different colors. So the methyls there are going to give us the same product. Okay, they're both methyls, but the one in blue is going to give us a different product. I'm going to draw the two products. The two differences between these alkenes is one is tri-substituted and this one's di-substituted. Our alpha carbon was here. That was our alpha carbon, right? And our beta carbon was here. There's our blue beta carbon. And I'm going to draw in the green beta carbons too. All right, so what's the difference between these two? Well, it depended on which beta carbon this base plucked off a proton. Notice here that the one that's tri-substituted used the blue beta carbon, and the one that's di-substituted pulled a proton from one of the green beta carbons. What I want to do is think about what selectivity we expect to see and what actually happens in the lab, all right? So let's draw out our hydrogens. I'm going to do this in purple here. On the, oh, no, I'm not. I'm going to do this in the correct color corresponding to the beta carbons. Let's draw out our 3 protons here. Okay. Now we have that other methyl. There's 3 protons here. And let's draw out our protons on this other beta carbon. There's just 2. So if we were just to think about the possibility, just the statistical mixture that we would assume. So just the number of H's. To get the tri-substituted one, we would have to lose a proton, a blue proton, one on the blue beta carbon there. So we only have 2 protons here. And for the di-substituted alkene, it came from one of our green beta carbons. There's a total of 6 protons there. So we have about a 1-to-3 ratio. So if we were to run this reaction, we would expect around 25% of our tri-substituted alkene and a whole lot of our di-substituted, about 75%. Well, guess what? That did not happen. All right, so when they ran the reaction, what happened? So this is actually in lab. This is what you're looking at. You actually get 70% of the tri-substituted and only about 30% of the di-substituted. I'm going to write what is actually observed. You're like, what the heck is going on here? So statistically, this doesn't make sense. I'm going to give you a rule. This is called Zaitsev's rule. which means that the most stable alkene, or the most substituted, is typically formed. Is preferentially formed in elimination reactions. Now, Zaitsev's rule is kind of like Markovnikov's rule. It's just a rule. It doesn't really talk about why. So we're going to talk about why, and we're going to use a potential energy surface diagram to look at this. One of the things that you will notice, though, is that we see the most substituted is preferred. Remember when we talked about alkenes, we've talked about how the more substitution, the more stable the alkene is. So a tetrasubstituted alkene is lower in energy and more stable, all right? Let's take that same reaction where we got two different alkenes, and let's look at the energy diagram here, the potential energy surface for this reaction. Energy here is on the left, and then here we have the progress of our reaction. Now, our starting material is going to be here on the left. This includes our ethoxide. Remember that the reaction is an E2 reaction, bimolecular. Both the starting alkyl group with the leaving group and our base is going to be in this rate of this reaction. We can also kind of guess that based on the mechanism, which is concerted. Okay, and we can also fill in the products that we have here on the right. We know that a tri-substituted alkene is more stable than a di-substituted alkene. Now, both of these will also have ethanol because the alkoxide, or this ethoxide, it picked up a proton. All right, so we have our starting material and our products. Our products are lower in energy here. We've got a carbon-carbon double bond. This heat of formation of this compound is lower. So let's now look at the transition states, okay? It's a concerted reaction, right? It is bimolecular. So what does this potential energy surface look like between the starting material and the product? Well, the easiest way to tell is looking at the mechanism. And so my question here is, when we look at this mechanism here at the bottom, when we look at this mechanism, you just ask, did it form an intermediate, right? And the answer is no. The mechanism is concerted, okay? Now, it does have a transition state, but there's nothing like a carbocation that formed. Remember the SN1 reaction, we formed a carbocation, so we had an intermediate. No intermediate here. This is simply just going to show one hump, okay? Now notice here, this is our rate determining step, our delta G double dagger. These are both transition states. I'm going to now start to recolor some of this. So sorry if you already chose your colors. We're going to get in here and recolor them. I'm going to change this dye substituted one to a green, and you're going to see here just a minute why. So here's our rate determining step for the tri-substituted, and the rate determining step for our dye substituted is higher in energy. This means the transition state is higher in energy as well. Let's think about this transition state, all right? So what I'm going to first do is I'm going to rotate this molecule, okay? So I'm going to rotate this starting molecule. And I'm going to rotate it so that our hydrogen and our bromine are opposite and anticoplanar, okay? So this is our alpha, this is our beta, all right? Our beta carbon, we have a methyl here. So I'm going to draw this wedge, and this proton that's on the beta carbon, this other proton is going to be dashed. On the alpha carbon, remember we had two methyl groups here. Okay, cool. So once you rotate it, it's much easier to draw in your bond breaking and making here. So I'm going to break these sigma bonds and I'm going to make them dotted lines to signify that this bond is breaking. So a dotted line is different than a dashed line. The dotted line means it's breaking. Now at the same time, so I'm going to draw this pink dotted line. That might be easier. We're also making that double bond, right? Let's draw in our ethoxide that's doing all the hard work here for us, OET. Okay, so this is our transition state. Now, the transition state that I'm showing here is showing that there's a partial double bond. We know that a more substituted alkene is more stable and lower in energy. So when our transition state for this tri-substituted alkene, showing that there's this partial double bond, that's why the energy at this transition state is lower than the transition state for the di-substituted alkene. That's because our transition state involves this partial double bond, all right? So when the reaction is happening, essentially this ethoxide is like, I want to get to the products and I don't want to work too hard, okay? I'm going to go over the smaller hill. That's exactly what it thinks. If an ethoxide could speak, that's exactly what it would say. I'm sure of it. And so when you look at this, we know the starting material, we know the products, we know the relative energies of the products. And because we ran the reaction and we saw that this was around 70% and the dye only gave us around 30%, we can use this to explain the energies of the transition states. Pretty cool. And this all goes in line with how a double bond that's more substituted is more stable. So this is the potential energy surface for an E2 reaction. Again, it's concerted. And that, I think that does it. Yep, that does it for our E2 intro here. Now, next up, we're going to get into situations where E2 or SN2 could happen. All right, so we're going to dive into that as well. And we also have one more elimination reaction, the E1 reaction, which will be coming up soon. All right, that's it for this video. I will see you in the next video.